interested in. Okay? An inverse function. First of all, you're all familiar with inverse operations. Inverse operations, which is different from an inverse function, but an inverse operation is like plus and minus. Plus and minus cancel each other out. If I add 5 and subtract 5, they cancel each other out, nothing happens. Multiplication and division are inverse operations. They cancel each other out. If I multiply times 10 and divide by 10, I've done nothing. And finally, squaring and square rooting are inverse operations. If I square a number and then square root it, I end back up where I was. And when you get to calculus, a derivative and an integral are also opposites, and they cancel each other out as well. Inverse operations cancel each other out. Now, an inverse function means you want to work backwards. Given an output, what must my input have been? That's the question. Everyone, I'm going to say it again, just in case you didn't hear it. An inverse function says, given a particular output, what must my input have been? That's what we're wondering. So watch this. Here's a normal function. I'm going to tell it to you, and you guess what it is. 0 becomes 0, 1 becomes 1, 2 becomes 4, 3 becomes 9, 4 becomes 16. What's my function?
X squared.
Yeah, my input is x, my output is x squared. Now, here's what an inverse is. Everybody watch very closely. Everybody. An inverse simply reverses the role of input-output. Literally, all I'm going to do is just switch the two columns. So now my inputs are 0, 1, 4, 9, 16. And my outputs are 0, 1, 2, 3, 4. So that's all an inverse does. An inverse switches the columns of input-output. It reverses the roles of input-output. So now what's my function? You take this input, how do I get to the number on the right? Square root. So what this tells us is that x squared and the square root of x are inverse functions. So f of x equals x squared and f of x equals square root of x. Those are inverse functions because it reverses the role of input-output. That's the key definition, reverses the role of input-output. Now, it also happens to be that square and square root are also inverse operations, and that's related. You know, the fact that they can cancel each other out means that they can reverse each other as well. Okay, so that's a lot of lead-up ideas to what we're talking about in chapter 5. Okay?
What was the last part? Reverses the what?
Reverses the role of input-output. Yeah. And you know, it's just a simple twist of language. If I say, if I work 5 hours today, I can make $50. Or you say, if I want to make $50 today, how long do I have to work? Right? It's just the difference of how we ask the question. Okay.
Did we already turn in the...
I just have a little pile up here. And if you haven't given it to me yet, folks, you can bring it up to me during the break. Okay, so where are we? Here we are. We have today and next Monday to cover chapter 5. It's only 5.1 and 5.2, not 5.3. So we have today and the next time to do chapter 5. And then after that, we have 3 class periods to do chapter 6. And then we have a test in chapters 5 and 6. Notes. I will grade all the tests this weekend and post your grades, so you'll be able to see your grades this weekend, but then I'll give you your test back on Monday. Anybody have any questions about anything? Yeah?
Did I miss anything in the beginning of the class, like this past Monday's class?
Well, Monday I wasn't here, unfortunately,
Yeah,
so you didn't miss it.
It was kind of weird because I was
Yeah, you were. Well, Hector showed up.
Yeah, thanks for reminding me.
Yeah, everyone had their own reasons for why they couldn't be here.
I was like, I wasn't sure if like I was just like.
No, you didn't miss anything. I sent an email out over the weekend. I don't know how many of you got it, but I sent an email saying that I couldn't be here.
Okay, for sure. I just got it that day. I didn't miss anything.
No, you didn't miss it. All right, then let's go and get started. My joke for today, I don't know if I told you already. Maybe you've already heard it.
Not sure.
What?
No, I'm just kidding, my bad.
What? You call cheese that's not yours?
No, I'm sorry.
Gabriel? Is it cheese?
Nacho cheese. Go ahead, Gabe.
Nacho cheese.
Nacho cheese. And what do you call cheese that you really like?
Or cheese?
Gouda cheese.
Oh,
It's really good.
Gabriel couldn't help himself.
What?
He couldn't help himself this time.
Yeah, I mean, it's such a good joke. And you had a really fun one. Well, you want to tell one of the ones that you just told me?
Which one? The one with the baby?
I don't know. The one I liked.
How do you put a baby astronaut to sleep?
Oh, yeah, that's a good one.
Permanently? Rock.
No.
Something about a rocket.
Not permanently.
Good.
How?
You rock it.
Yeah. Related, how do you plan? Wait, no. How do you throw a party in space? You plan it. Those two jokes go together.
Nice.
What do you call an elephant that doesn't matter?
Irrelevant?
Elephant.
Irrelevant, yes. Okay, folks, so here we go. So, chapter 5 is all about function composition. I want to make a note about that notation right there real quick. So, I remember very clearly, I was in 8th grade. It was March 27th. It was 10 a.m. And we were working on functions. And who knows what the function was? It could have just been like the function x squared plus 5 still. And we were working on functions, and our teacher was just giving us numbers to plug in. And they, they said like 3, and then I plugged in 3 squared plus 5, and that's 9 plus 5, which is 14. And then the teacher was like -7, and so I plugged in. I was like -7 squared plus 5, that's 49 plus 5, which is 54. And then my teacher said, A. And I remember the day. My brain exploded. I was like, what? I thought she made a mistake. I thought she wrote something down wrong on her paper, and then she did something wrong, and I was about to raise my hand and be like, I'm sorry, you can't plug in a letter. It made no sense to me because you can't compute anything. So she came over and she said, well, yeah, just write it down. I was like, write it down? That's not very satisfying. That's lame. It's just a squared plus 5. I wanted an answer. She says, you don't have to get an answer. It's just a squared plus 5. It was very strange for me.
I have a question.
Yeah.
And there's your lesson in life.
Yeah.
What about if you have more than one variable, like A and C?
Well, you want to plug in both of them?
Are you doing like A plus C?
Like
Oh, yeah, sure. That's great. So, like, what if it was A plus C? Then it would be A plus C squared plus 5. I'm still going to use the same structure over and over. The structure of my input or my output is going to be something squared plus 5. And it doesn't matter what I write right there. I just put it right there. So you can go, pretty far with this.
A squared plus 2AC plus C
You can put
squared
anything.
plus 5.
You can put a happy face.
Oh.
And I don't care what it means. It's correct. Right? So that's correct. I can put in, you can put anything into a function. It may or may not mean anything valuable, but I can write cat.
Are you gonna do that on the test?
No.
For extra?
No. Well, the point is that's how a function works. And that's why it's so important to understand this notion of writing a function empty. Because writing it empty gives you the structure of the function, and then you can plug anything you want in. Like Emily. Yeah, that's totally valid. You can do it. Again, what meaning is it? I don't know what meaning it is, but it's correct. Everyone in the mathematical community would agree that that's correct. So, all that said, what else are you allowed to plug into a function? And then this is where it's really good. What else can you plug in? What else can you plug in?
X times B.
Yeah. Another function. Right? And then it's like super exciting. Yeah, and now that's function composition. I plugged a function into another function. So you'll notice, I'm not adding the functions together, I'm not subtracting them, not multiplying, not dividing. I'm plugging a function into a function.
And that's the answer?
Yeah. This is like function inception. You know that movie with Leonardo DiCaprio, Inception, where he goes to bed, he starts dreaming. In the dream, he lays down on a bed, falls asleep, starts dreaming. Lays down on a bed, goes to bed, falls asleep, starts dreaming. So he's having a dream within a dream within a dream. That's never happened to me.
That has happened to me.
Isn't it called something called someone else is dreaming?
Lucid dreaming.
Thank you.
Okay, so you don't have to stop at 2. So if you could do f of, and then plug in the function g. What can I plug into g?
H.
Anything else? Another function. Okay, so function composition is embedded functions. It's plugging in a function and a function and a function, like a turducken. I don't know if you guys watched Friends or maybe you've heard it some other way, but there's a turducken, which is when you put a turducken.
Joey.
I think it's a turkey.
Yeah.
And then inside the turkey is a duck, and then inside the duck is a chicken. Yeah. So you've got turkey on the outside, and then a duck, and then furthest in is a chicken. I don't know if we should go worse. Anyway, so you cook that whole thing in the oven, and then you eat it, and that's a turducken. Well, so that's function composition. You're plugging one into the other. So that's all chapter 5. We're going to cover that today and next time. Chapter 6 is moving on to a wonderful, huge idea called logarithms. And so you all know exponential functions like 10 to the x. An exponential function is pretty straightforward. It's like 2 to the power of x. So if I have 2 to the power of 5, that just means 2 times 2 times 2 times 2 times 2, which is 32. So exponential function is pretty straightforward. You just multiply over and over and over again. But then what if I asked you 2 to the power of what would equal 50? Right, I'm going backwards. I'm saying, if I give you the input, you calculate the output. But what if I give you the output? I want you to figure out the input. And that process of solving for an exponent is actually called a logarithm. So logarithms is an entire field of mathematics which simply states find the exponent. That's it. Logarithm means find the exponent that you would have to input in order to create a given output. So that's what chapter 6 is. It's looking at a particular instance of inverse functions. Exponential and logarithms are inverse functions. They would cancel each other out, and they reverse the role of input and output. Okay, so that's where we're going. Anybody have any questions about where we're going? You're all super excited. I know you're like, woo, we're all done with synthetic division, polynomials, rational functions. Let's get us some function compositions, inverse functions, and exponentials and logarithms. Yeah, so everyone look at 5.1. Everybody have their notes? So first of all, can you see up at the top there that they also drew that same picture I did? That you have function f, so input into f, output from f, and then you take that output and make it an input into g to arrive at your final answer, g of f of x. Or you can create a new function that simply takes the original input and goes all the way to the final output without stopping halfway to calculate another input-output. Okay, so that's function composition. Now everybody, you should write this down with me. They have a particular notation. And can I just tell you this? I'm asking pretty please, but I'm also ordering you. Write down everything that I write down. Because when I did this morning, people wrote down all sorts of things that weren't what I was writing down. I was like, folks, I really need you to write down the notes. So just a friendly reminder to actually write down the notation that I'm writing down. You might know this material from before. So if you do, still at least write down what I'm writing down a couple times. And then that way you're getting familiar with my notation. Okay, so right up at the top it says composition of functions, and it gives a definition. The first definition is f circle g parenthesis of x. That's a new notation, for us anyway. You might have seen it in your former life. And that little circle is not a plus, minus, multiply, or divide. It's a circle.
In my former life, I was a chicken.
You were a Sudoku? So that little circle means composition. Don't know how they came at that symbol. But it means composition. And what that means is you start with the function f of x, because f is first. F is the first letter. So you're taking your function f, and what are we going to plug into it? G of x. So we're going to plug in g of x into f of x. I find it very helpful, and I'm going to write it again and show you so you can see how I exaggerate. I find it very helpful to write the first function big. So it's f. And what am I going to plug into it? G. Okay, so f is the function, g of x is the input. Now technically, x is the input into g of x. And then the whole g of x becomes the input into f. So if you were to say, what's the original input? The original input was x. But it's passing through the g function to get to the f function.
Wait, what's the difference?
Huh?
So you
We're
plug
solving for fog.
Oh,
Yeah, this is the definition. The definition of f circle g is you take the f function and you plug as an input g of x. This is the definition. Yes, the straight up definition. So likewise, if we were to say g circle f of x, now the first letter is g, so we're saying take the g function, and what should we plug into it? F of x. So, you know, without any experience yet, you might say, well, isn't that going to be the same thing if I plug g into f or plug f into g? Could that be the same? It could be. They could end up being the same thing. But they might also be very different. Much like cooking a turkey and a duck versus cooking a duck and a turkey. It would be a different flavor profile, I'm sure. So the order really does matter. Now sometimes they do equal each other. Sometimes f of g of x does equal g of f of x, and that's very special. But it doesn't always happen.
If you ever get confused with it though, you can always think of it as like building a house. The first one, like the F talking about G, the F is your base, and your G is your walls and everything else.
Oh, okay, sure.
Right, and I think about it like building a bed.
Then your X is your actual finisher inside.
Yeah. So here's what we're going to do first. Let's take these definitions. We're going to do number one together. And what I'd like you to do, I mean, I have to write it. I suggest you write it too. F of x equals x squared. And then g of x equals 2x plus 1. I always find it helpful to rewrite a function in my own writing, even though you're staring at it, you're like, Mr. G, it's right there, why would I write it like that? But see, it's like the power of ancient cultures when, like, if you know your enemy's name, you have power over your enemy. If you write it down in your own handwriting, you gain a little bit more power over what's happening. So I've got a squaring function, and then I have a double it plus 1 function. And I'll even go so far as to write it empty. So f something equals something squared, and g of something equals to something plus 1. Just as a little helpful, so I see it. That's the structure of the function. That's the structure of the function. So what do we want to do? Part A. I would like to calculate g circle f of 0. So remember, g circle f is our new function. It's our composition function. Anytime you see g circle f, you're doing the function that goes from the original input all the way to the final output, skipping over the middle guy. That's what we're doing when we do g circle f or f circle g. You're going from the beginning input all the way to the final output. So you don't have to take it in 2 steps. So, everybody have this down? First thing is you rewrite it according to the actual definition, which is big G, little f. Oh. Okay, so G is my big function that I am inserting f of 0 into. So, what would we do first? We have to go find f of 0. So what is f of 0? What if I plug in a 0 right here? Yeah, just 0 squared is 0. So I'm going to replace f of 0 now with g. Sure. Because f of 0 is 0. And how did I find that out? By looking up at my function. If I plug in a 0 into f, it would just be 0. So I replace the f of 0 with g of 0. F of 0 is 0. So now I just have g of 0. So what's g of 0? I go up and I look. What happens if I plug in 0 right here?
0 plus 1.
Yeah, 2 times 0 is 0 plus 1 is 1. And so the answer is 1. So what this means is that if I plug 0 as the original input, the final output is 1. We skipped over the middle step, and we went straight from the beginning all the way to the end. So again, I'm asking very kindly and nicely, write it down in this notation, because this, if you've never used this notation before, it's important to learn new languages or new notations, because you'll see it in textbooks, you'll see it on more. And even if you do have another way to solve this, which is fine, write it down a couple times. Okay, so let's try that again. Let's do part B. Part B is asking f of g of -1. So f circle g of -1. So what do we do? The first letter is f, so I'm going to write f really big. And then the second part is g. I'm going to write that tiny, g of -1. So what's the first thing we compute? And we need to compute the g of -1 to know what we're plugging into f. So what is g of -1? I go up here. What happens if I put a -1 right there?
-2 plus 1.
Yeah, 2 times -1 is -2, and -2 plus 1 is -1. So that now, that part that's in there becomes -1. That's your dumb luck. The g of -1 was -1. The input and the output were the same. Now, what's f of -1? I'm going to take -1, plug it in right here. What's f of -1? Yeah, -1 squared is -1 times -1 is +1. And so that final answer is 1. You're noticing that what you're writing down, you have the original problem statement, you have the definition of what that problem statement says, and then you compute the inside, and then you compute the outside. It's always going to, you're computing the inside, then you compute the outside. Let's try another one. C. It says f of 2. There you go. Now notice the way I'm saying that. It's f of f. The little circle, we don't say f circle f, we say f of f. And furthermore, of -2. I mean, talk about a lot of ofs. F of -2. It's a very strange use of language. I want pizza of pepperoni and of sausage. Okay, so by definition, that means the first letter is f, so big F. And what am I plugging into it? F of -2. So you go find out what f of negative 2 is. If we go back to my original f, if I plug in negative 2, yeah, negative 2 squared would be 4. So that's my input that I'm putting in. And now I'm putting 4 into f, so I go back to f and I plug in 4. Yeah, 4 squared would be 16. How does everyone feel about this so far? First of all, what you're writing down is lovely. It's beautiful, gorgeous, really nice notation. You know, at first it feels weird, and after a while, it's just a notation. My sister came up with a brilliant quote about avocado. She says, when you first try avocado, it really doesn't taste like anything. But after a while, it starts to taste like avocado. What? Yep. And you know what? That's math. Sometimes you're writing down a bunch of symbols. You're like, what is this? But after a while, you've written them down so much, you're like, that's how you do it. That's math. Okay, D. F of G of a half. So F circle G of a half. So again, the first letter is F. I write that nice and big. Second letter is G, so it's G of a half. We have to compute the inside first. So G of a half, I go up to my G function and plug in a half. So that'd be 2 times a half plus 1. Half of 2 is 1, 1 plus 1 is 2. So now I have F of 2. And now I go plug 2 into F. So I plug in 2, that'd be 2 squared, so that's 1. Anyone, would you like to ask any questions about what you're seeing here? It's a lot of symbols, isn't it? You might be looking at it and thinking, man, this is why I would never use this in real life, or something like that. I don't know. Because it's so much symbolic notation. But, all right, so I would like everybody to go ahead and try number 3.
Using the same ones at the top.
Yep, right, yes. You're doing number 3 with these 2 functions, but you're still going to do A, B, C, D from the top. So go ahead and try number 3. Try to write it down exactly the way we just did. I will tell you that part C is going to feel awkward. Like you're going to see it and you're like, well, that's weird, because it doesn't simplify. But that's okay. The key thing is not to try to figure it out. The key thing is to write it down. The key thing is to follow the steps. So long as you follow the steps, it's okay if the answer looks a little weird. And then if you write down enough answers that are weird, they all become normal. And avocado tastes like avocado.
You gotta put them together.
Hmm?
You gotta put them together.
Hello?
You gotta put them together. Like we did. Get all one. What are you talking about?
Yes. Oh, I think that's the next page, where we actually are going to merge the functions together. Yeah. We'll do that next. Yes. So you're doing this first one, right? So make sure you put on 0. Yeah, that way you see it. Yeah, that's the correct way to start. Recall your first step is just to write down A, the problem. So the problem is G circle F of 0. Always write down the problem. And then write down what it means. The definition is G of F of 0. And then go find out what those are by plugging 0 into F. So in this first one, folks, what happens if I plug in 0 into F? Yeah, 3 minus 0 is 3, and the square root of 3 is just the square root of 3. You can just leave it in the square root of 3. So the first one now becomes G of the square root of 3.
The square root we cancel from the square, or no? No.
Yeah, potentially now. Okay, so now we're plugging in root 3 into G. So if I plug root 3 into x squared plus 1, now this is where you might want to use a little scratch work. Right? Humans are not designed to do all this in our head. I would need to do a little scratch work and say, well, if my function is G of something equals something squared plus 1, and I plug in √3, then what happens when you square a square root? They cancel out, so that's just 3 plus 1, which is 4. So g of √3 is 4. Nice thing. Okay, so yeah, very nice.
So it is like. So it's. Like,
Nice. Now have you? I know that right now you're doing it in what feels most comfortable here. All these little arrows as you're like, okay, now get down here and go down here. You know, what if you try one where you go all the way across? Just try it out. Just see how that goes for you. But see, I see why you're doing that probably because then you're able to follow visually from one to the next. So here's another suggestion for you. If you like doing it that way, then why not just make it a perfect vertical stack?
Right.
So like the one that we're about to do, F circle G of -1. Then right below it, just F G of -1. And then right below it, G of -1 would be 2. And then right below it, like that. So then it's boom, vertical stack, no need for little arrows.
Right. Yeah.
Because you're not even doing, I mean, you don't even technically, I mean, you could go like that.
Right.
But oftentimes when people work vertically, they don't even bother with equal signs because you're just showing a progression for it.
That makes sense. I think
Yeah, just try something and you know, just try it out. See how it works. Okay. Good. So you have your F circle G and F of G -1. My G of -1 became 2. Yeah, very good. Yeah, well,
because like this is
what's right?
when you want there.
Yep, absolutely.
One, just one, but that's 2.
Absolutely. Yeah, you're doing it. Eddie, I really like how you started this off by having it there and then putting the F of and the F of. It's just a really nice way to just structure your work because now you know you're just plugging things in. Yeah, I have to admit, I kind of do things that way. Is it working now?
Oh, okay. Is this right?
When you plug in 2 and a G, oh, okay. Oh, yeah.
No, I mean this one.
That just seems so low.
Okay. You don't simplify it.
Well, you can simplify the square root of 5.
Serious.
It doesn't simplify. It's just a decimal 2 point something. But you want to just keep it as root 5.
We have actually a whole number of times self duty. So that agree. This is square. What did Mr. G say about square and square? So, finding the number C, we need it.
Yep, that's totally it.
Okay, right there.
Yeah, it doesn't simplify. You might be able to rewrite it in some other form, but it doesn't fundamentally simplify.
You have 7 squared.
Yeah, that's the answer.
Right.
That's it. That's the one that I said was weird.
What's 7 squared?
Hey, real quick, did you finish this one? Where's the, what is that?
7 squared? Oh, sorry.
Yeah, plug 2 in the F and see what you get. Yeah, very nice. That's it. And again.
No, wait.
Yeah, that's true. That's root 5. So now you're going to plug root 5 in for X. And so you can start by writing root 3 minus. You know, write the structure of that. So big square root 3 minus. And then you just put root 5 right there. Yep, that's it. That's totally it. It looks weird,
Yeah.
but you followed the rules. You did what you were supposed to. You took that function, you wrote it empty, and you put the root 5 in it.
So,
Yeah, that is correct.
so and then.
No, I forgot it. If I forgot it, I mean I lost both of them.
Oh.
I need to get some new ones.
Extend. So then this one is, that's right.
Right.
Right, so. It'll put a frame.
So we're dealing with. It's okay.
You have square root and square root.
And you can square root is square root. Well, I mean, you can sometimes, but in this case, it doesn't simplify.
You said number 3 would be kind of weird, right?
Yep.
So.
So it would be square root of 3 minus square root of 5.
That's exactly that. Take a look.
Yeah, because the one you said it's gonna be dropping out weird, I was still doing B. You told me that, so. I thought it was like,
It is weird.
B is weird?
Oh, no, sorry, B is not weird.
Yeah,
C.
because that's what you told me when I.
Oh, I'm sorry, I was thinking about the root. Folks, you're all doing great. Making great progress.
He was saying, you have F, you have F like this, right? I'm gonna say just. What is it? So. Yeah, that's right. So you said you have F. G. 1. Yeah, so our F. So you got.
And decimals.
Oh,
Radical of 3 minus X, right?
I thought half squared was one at first and it wasn't.
Do what?
I thought half squared was a one, but it's not. It's 0.25.
Right. A half times a half would be, and if you write it out,
Yeah.
it's more obvious.
Yeah,
One
it is.
half, and 1/2.
Right.
So you're gonna
It's
say
the 1/1.
Yep.
That read.
minus.
Yeah.
Nadine, how did all that feel? Huh?
Yeah.
I mean, a little awkward or weird, but you did it. You did it. Yeah, really nice work. How you feeling, Lloyd?
So they.
Excellent. Hey, your work was really good.
3 minus G of, or G of negative.
How did that feel trying it the other way?
A lot better. I feel like I'm like.
Which one did you do? You did
This
G
one.
of G. And so you started here, went to there, went to there,
Right.
over there.
So
Or just, this is like more like scratch.
what
work.
is, what's
Oh,
the
okay, kind of simplify.
Yeah.
So technically you went here to here to here.
What's this?
Oh, to there. Okay. Yeah, so I would just recommend that you try to be as consistent. Either go completely downward or go completely sideways.
Okay.
I have to admit, I'm not perfect at it. Sometimes I do a little bit of diagonal work like you're doing now. It's just harder on your brain and your audience.
Yeah, but when I'm.
Now-
Like when I'm saying.
This guy.
Where did I go?
Start?
Really nice. Okay, folks.
You should color code.
Yeah.
Yeah, color code
That's
stuff.
1, where, plus 1.
Oh, she just found more races. Is that what she did? Oh, she found more races.
Staples.
Oh, yeah. I'm gonna try a new race.
Yeah.
What is,
Yeah,
answer your question?
for practice. I mean, when you did it, it was fine. But then-
Well, can I say real quick? One thing that I would suggest is you're kind of mixing your notation right here. I would go strictly with what we're doing right now as an example. And the example would be that you first write down the definition, which is f of something. And what are we plugging into it? G of -1. That's the first step. That's the definition. That's the definition at the top of the page. Is to change the circle notation into this notation. So that's what we did, change the circle notation into this. Now you're gonna go look for what is G of -1. So you go up to where G is, and if you want to, show some work over here, say G of something equals something squared plus 1. And now plug in what they're asking you to plug in, which is -1. And now go ahead and compute that. -1
negative 1 times negative 1.
What is the
1,
fraction form?
and 1 is
plus
2. So now that thing right there is going to become, notice the f of something stays. The f parenthesis stays. I'm just going to replace.
Now what we just did right there was plugging in numbers. Numbers are nice because you just plug them in and you compute them. Even though you can't necessarily compute all of them, like that one that was the square root of 3 minus the square root of 5. Nobody asked about it, but let's just talk about that real quick. What is the answer? It's the square root of 3 minus the square root of 5.
Isn't D also weird?
What was D?
1/2.
Oh yeah, the square root of 1.75?
Yeah.
Yeah, that is a little weird. So let's talk about that. If you just have that answer, first of all, that is the correct, exact answer. It is exact. If you type it into your calculator, you would have 0.8740320489. Is that correct? Is that the answer?
You can simplify it, I guess.
You mean you could round it?
Yeah.
Yeah, you could round it.
The calculator gave it.
Yeah, the calculator gave it, but the fact is, that's not all the decimals. There are more decimals. How many more decimals? Infinitely many. So is this the correct answer? No. It's an approximation. It has, 10 decimals. And if you were to round it to like 0.87, no matter what, everything that I just wrote down right here is a lie. Yeah, it's not the answer. This is the answer. That's exact. That expression contains all infinitely many decimals wrapped up inside of it. This expression only has 10 decimals, that expression only has 2 decimals. Now, if all we're trying to do is compute how much money you owe me, and you owe me 87 cents, that's fine. You got the answer. Give me 87 cents. But if you want to know like the exact decimal places out to infinity, then this is the answer. All right? Okay. I tell you what, since that just kind of completed a thought right there, let's just take our break now because my phone just went off. And then we'll come back and try something else. So the time is 1:30. Let's be back at 1:40.
Oh yeah, I heard
I do want to check
on Canvas again.
What?
Yeah.
Yeah, I always record.
Yo, this is.
Where do you find where you're clicking on?
YouTube.
Oh, YouTube.
No, I mean it's on my Canvas site. If you just go to Canvas to announcements, I have an announcement that says course videos.
Oh.
This is. This is right.
I think we're going to.
I don't know where you This is not my.
So it will be slant. Well, it will be a slant, right? I'm gonna- It's gonna be slant. It's gonna be slant. Well, go ahead and start off.
Okay. The whole circle?
Yep. Of course.
asking for the vertical aspect.
What's that gonna be? Okay.
But I'm having problem with how to find the slant. It's
Right.
good.
So let me ask you this, how do you know if it's a slant?
Looking at, like a big green,
So the degrees are what's like the leading,
Yeah.
the leading, right?
yeah, because I know that if there's even, they're asking me.
Right, okay. If it was just this, that would be one negative.
Yeah.
Well, because of this. you have to know that.
See,
So now let's go ahead and write up the division of how what you really.
oh my God, I'm really fucking I'm serious, I don't think it's so calculated. I need something.
And that's why I told you. And that's why I do what I do when I get something. Okay, so now, the only thing we're really concerned about honestly is if this guy replaces this guy.
Yeah.
We're gonna put that guy right here.
Okay.
Okay, so what do we need to make this 2x and then 12x squared?
And then 1x, right?
You tell me. Yeah, okay, so where you, let's put that there. Now, what we're gonna do is we're gonna multiply this whole thing to -3 first.
Negative 3 first.
Actually, you know what? Let's go, I do it, I just do it, you guys are supposed to do it, it does it like this, right?
Yeah.
So let's do it just like that.
Okay, so 6 times 12 is, 6 times 2 is 12, and then x times x is squared, so 12x.
Okay.
And then so,
Before you do, but before you do that completely, let's get this other part. You're gonna do all,
okay.
everything all at once.
Yeah, you're right. That's why I was thinking that. So, negative, it's negative.
With the questions you should do, someone asked you.
Mm-hmm.
I think you wrote an
What we're
error.
gonna do here.
I might have. Where?
That problem, can I use the paper for that problem you have? Hey, no, that's the paper that problem you have? This one you're doing right now.
That's right.
Don't put your equals, don't put your equals. Do I have to do this, I don't know, what am I doing here?
See
Yeah.
that's what, see that, like, how did, like,
We're subtracting the entire thing.
Oh, where is this? Oh, the practice test?
yeah, I think it is.
Divided by 20.
So what are you saying my error is?
How did?
Oh, that is an error. Yes,
Yeah.
yeah, correct.
Yeah.
Yeah, that was a
She was
typo.
talking about that too, because how did, like, she make sure she's trying to get to, if this is an error, that must mean the problem, the answer is wrong, right?
No, because we're still just curious to know, find the equation of the vertical asymptote and the equation of the slant asymptote. The vertical asymptote is still that, because you just set 2x minus 3 equal to that. And the slant asymptote is still this part up here,
Yeah.
not this part.
Okay.
So the slant is still 6x. That was not impacted.
Okay.
Yeah.
Alright.
Yeah.
Okay.
You're left with 2x.
There we go. Alright, now, let's do that. What, how do we make this back?
It goes into a 1, right?
There we go.
So it's plus 1.
Mhm.
Then you do the same thing and multiply.
Well, we're gonna drop this guy down. Okay, I like bringing the arrow down, so stay down. I'll bring that up. Right? So I bring down, I drop the arrow, I write this up. Now I'm ready to put this with this. So you said you had one for this to look like that, right?
Yeah.
Okay, now let's go a little bit.
So,
That way I have to put a little bit here.
now. This one. Now when you're dealing with slants, when you're dealing with the long division, yes. Deal with slants, you know. So what do you have?
That's like, yeah, 0 right here. Zero. Is that how it's formatted? Or?
So.
Just like that. So why? So always what is it?
As long as it doesn't give you like a remainder, right? As long as it gives you,
So he doesn't worry about the remainder.
right, so you just keep going until it either completes all the way, or if it gives you a remainder. If it doesn't give you, a remainder, back.
Oh, okay. I know, I was having trouble with this one, but then I searched it on how to do it, and I didn't do mine. And I was like, how do you do it before? And then I just searched up on the wall, and it turns out like, to simplify it, and I'm doing
Because if you have a negative one, what's that radical? That becomes an
Yeah.
That's squared. Seven times seven. Yeah. 9. That becomes 7. That's so this, right? Like this. So
But this one has the I.
right. So you just keep going. You find out.
And I actually tried it, and I was like, it makes sense. You do long division, and then this one has the division, that's what you have right here. And then you can grab the one on I. You want me to show you?
Yeah, good.
Okay. And just look. So
Oh, these races are nice.
I'll have to find her.
I think it's on the.
Oh, good.
No, it's weird, but it did help me a lot. I don't know, I just searched up the Google.
All right, folks. Let's proceed. Let's take a look at the next page. We're going to try plugging a function into a function directly without actually plugging any numbers into it. We're just going to plug a function into a function. Kind of fun to do. So, same thing, I'd like you to try writing this down the way I write it. And if you have another way of doing it, I'd love to see. But everybody try this together. So first of all, take a look. It says, use the given pair of functions to find and simplify expressions for the functions. Oh, and state the domain. We'll go back to the domain question. Let's just focus on actually doing the composition. So, for number 5, everybody, go ahead and start by writing down the functions. F of x equals 2x plus 3. And write it empty. F of something equals 2 something plus 3. And then write g of x equals x squared minus 9. And write it empty. G of x, oh, g of something equals something squared minus 9. All right. So these are our functions, and we'd like to compose them. And from our ABC option, you can see that what we're going to do is find g of f of x, or find f of g of x, or find f of x. And the only thing they didn't ask us to find was g of x. But that's okay. If we wanted to, we could. So notice that in the first one, it's g of f of x, whereas the second one is f of g of x. Order matters. So when we look at part A, when we write down g circle f of x, now everybody watch. I want you to try this as much as possible to match what I'm writing. If you have another color, even better, but at least exaggerate size. The first letter is G, so we're going to write G really big. And then the second letter is F, so we're going to write F really small. So G is the function that we're really interested in. And what are we plugging into G? F of x. So f of x is the input that we're plugging into the function g. Okay, so now here's what we're going to do. We're going to start by writing g really big, but the structure of g. So let's write down the structure of g now. So the structure of g is something squared minus 9. That's the structure of g. And what are we going to plug into g? F of x. Not just the structure of f of x, but the actual f of x, 2x plus 3. And so now we plug to f of x is 2x plus 3. We put that in. And that is the answer. We could be done. Right? Because that is the answer. We just plugged a function into a function. No, we are going to simplify. But that is accurate. This is the answer. It is correct. If you typed it into more, it would accept it. Anybody on the earth would agree that that's the answer. But a lot of times, if you do actually FOIL it out, the answer is even better. And that's what we're going to do. So let's FOIL that out. So doing the rest of our steps now, I'm going to drop down a line. That's really 2x plus 3 times 2x plus 3 minus 9. Now there's this whole question. Should I simplify? Should I not simplify? You should simplify if by doing so, it looks better than what you have. If it doesn't get better than what you have, don't bother simplifying. But the only way to know that is to simplify. And so simplifying gives you the option of saying, well, which one of these is better? So first what we're going to do is FOIL. So we have to FOIL that out. So first, 4x squared, outer, 6x, inner, 6x, last, 9, minus 9. And see right there, that's kind of nice. What happens to the 9s? They go, well, they cancel. Anytime there's cancellations in a simplification, that's good. That means that you probably are ending up with something better. So now I have 4x squared plus 12x. That could be the final answer. Because we've already FOILed, there's no more PEMDAS to do. But if we were interested in, going one step further, what could we do? We factor 4x out. So we have 4x outside of x plus 3. And ultimately, it just depends on how much you like the person who you're giving this answer to. Right? If you give them this answer, that's one possibility. Give them this answer, that's one possibility. Give them this answer, that's one possibility. Again, it matters how much you like the person. So for instance, if this person then had to take it and solve by setting it equal to 0, well, they would either have to set that equal to 0, solve that, or set this equal to 0, solve that, or set this equal to 0, solve that. This is obviously the best thing to set equal to 0 because it's already the zero product rule. We have something times something equals 0. Whammo. Anybody can now visually look at that and immediately say the only way for 4x equals 0 is if x equals 0. And the only way for x plus 3 equals 0 is if x equals -3. So if you like the person, you do that. If you don't like the person, maybe you do this. Because then you're like, haha, sucker, do this. And now they have to move the 9 over, and then they have 2x plus 3 squared equals 9. And then they have to square root both sides, and then they have 2x plus 3 equals plus or minus 3. And then you have to subtract the 3 over, and then you have 2x equals -3 plus or minus 3. And then you divide off the 2, and then you have x equals -3 plus or minus 3 all over 2. And then they have to split that into 2 possibilities. And then they would have -3 plus 3 over 2, or -3 minus, plus or minus -3 over 2. And then that would give them the answer of 0 over 2, which is 0, or -6 over 2, which is -3. So what answers did they get? 0 or -3. But this way was a lot nicer. Plus, I think you'd all agree that doing algebra that way took a lot longer than just foiling, factoring, zero product rule. To be fair, it probably wasn't any longer. Probably it's about the same. 6 to 1, half dozen to another, is that what it said? All right. Admittedly, I went a little further with that problem than is required. We found the x-intercepts by setting it equal to 0. We don't actually have to do that in these problems. All we really needed to do was just find out what the answer was, and the answer was that or that. Okay? So let's try another one, B. We'd like to find the function f of g of x. Now again, folks, you start by writing down the problem they gave you. F circle g of x. Then you use the definition. That means big F, little g. That could be a rap song. Big F, little g. I don't know. I'm silly. Okay, so now what? I'm going to write the structure of F. So big F becomes my structure. That's 2 something plus 3.
Big F will be by DJ Cal.
Yeah, there you go. And then little g, that's what I'm plug in. G of x is x squared minus 9. Okay, so there we go. I just plugged a function into a function. Function inception. Now again, at this point, you could be done. You type it into more, it'll take it. Anybody looks at it, they're like, yeah, that's correct. But you can simplify it. And again, it depends on how much you like the person who you're giving the answer to. So I would go ahead and distribute it and say that's 2x squared minus 18 plus 3, which is 2x squared minus 15. And that definitely looks better. 2x squared minus 15 is way better than that first thing that we got. So the last one was f of x. So we write the big F, and then what's getting plugged in? F again. So the structure of F is 2 something plus 3. And the thing we're plugging in is F, which is 2x plus 3. So again, yeah, we definitely want to simplify because it's all embedded and weird. We want to simplify that. So we distribute, and so now we have 4x plus 6 plus 3, which is simply 4x plus 9. So functions, we started class by saying what's a function? It's an input-output machine. What can you do with a function? You can plug something into it. A function is so adaptable, you can plug something into it, you can plug a function into it. So into a function, you can plug a number, you can plug a letter, you can plug a kitty cat, you can plug a turducken, you can plug another function. And that's function composition.
the square root of a negative number?
Yeah.
Oh, look at me.
In fact, that's interesting. You could plug an imaginary number into a function, and out might pop a non-imaginary number. In fact, that'd be a very easy example. Like, let's just say that it was f of x equals x squared. If I plug in an imaginary number, then it's I squared, which is -1. And so you could have a function that takes imaginary numbers and makes them real. Yeah. All right. Anybody questions before we keep going? Oh, in fact, are there more? No, that's it. Yeah, we could go ahead and do the domain. That's not a new skill, that's an old skill. Remember, the domain says input is all real, no, the domain is all real numbers except those numbers that cause you to divide by 0 or square root a negative. So in part A, are we ever going to divide by 0 or square root a negative? No, so the domain is all real numbers. In part B, are we ever going to divide by 0 or square root a negative? No, so the domain is all real numbers. In part C, are we ever going to divide by 0 or square root a negative? No. In fact, folks, anytime you don't do domain problems, all you're really looking for is the presence of a square root symbol or the presence of a denominator. If you don't have a square root symbol and you don't have a denominator, the domain is all real numbers. So even asking us to state the domain is kind of silly. Because in all three cases, the domain was an interval notation, negative infinity to infinity.
Are you happy with that?
And even with the radical, don't you want to make sure that it's an even radical? Where that you're looking for? No, like that catches.
Oh, yeah, sure. That would have to be an even number. Is that what you're saying?
Yeah.
Yeah, good point. Yeah, that's even more specific. Boy, I never specified that far. That's a good point. I don't think this will be on the test, but you should still remember how to do domain. Yeah, it'll be on the final for sure. Okay. Next. These next couple of questions are not computation heavy, but they require us to be flexible in our thinking of how we think about functions. A function is an input-output machine. It takes an input and pairs it with an output, which creates a coordinate. And a coordinate can be listed on a table of values, and a coordinate can be put on a graph. So there's actually many ways to think about a function, even while knowing that it's just an input-output machine. So everybody, take a look, and try this with me, okay? Try it out. Look at these 9, 10, 11, 12. Right up front it says, use the following functions and find the value if it exists. Now look at that notation up there. F equals curly bracket, coordinate, 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 curly bracket. Have you ever seen anything like that in your life? Once. Once. All right. The rest of you, nuts. Right? And then G equals curly bracket, a bunch of coordinates, curly bracket. Well, what is that? Well, that's a function. They're saying that's the definition of those functions. Well, first of all, remember, a function is an input-output machine. So if you look at F, this input-output machine will take in -3, out 4. Input -2, output 2. Input -1, output 0, input 0, output 1, and so on. So F is, in fact, just a list of inputs and outputs. So now try this with me. We all know that that's the definition of F. So now let's rewrite F as a table of values. It would just be listing all those coordinates, but in a table form. So now we have -3 input, 4 output. Input -2, output 2. Input -1, output 0.
Can we write this where we put our answer at? Or?
Yeah, write it. Just write it right there on the page where you have space. Ultimately, all we're doing is right now we're writing synonyms. What I just wrote, this table of values, is exactly the same thing as what they wrote. It's just another way of writing a list of inputs and outputs. Input, output. Furthermore, I could go ahead and take all those input outputs and put it on a graph. Because what is a graph? Just a list of inputs and outputs, but graphically, as points. So now I can go ahead and go -1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. And now I'm just going to list all my coordinates on a graph. So -3, 4, -2, 2, -1, 0, 0, 1, 1, 3, and 2, 4, and 3, -1. Now, that's just a bunch of dots. But it's not a nice, smooth, continuous curve. Fact is, I am ignorant of what the real curve looks like. You know, if F is something that I could graph on Desmos, I don't know what it actually looks like. I could take a guess. I could say, I think it looks like bounce. Okay. I mean, is anybody going to bet me money that that's not right? I mean, that could be it. Right. So for all I know, that's the function we're talking about. It's just some sort of cubic. It has, 1, 2, 3 points of intersection with a bounce. So it's just a polynomial. I'm just going to claim that it is. And all they really did was just give us partial knowledge of that function. Fact is, it's still a function, still a graph, and that's what we're looking at. Okay. So everyone wrote all that? Really, you guys did? You got a little graph too?
Oh, no.
But maybe you didn't. Okay. So likewise, we can go ahead and find G. I'm just going to do G of table of values real quick. You too. Just going to take that information and make it a table of values, just to try it out. Like thinking of a function as an input-output is such an important idea because a table of values is a list of input-output, a graph is just a bunch of points that are input-output. That if some math person ever just came up to you and asked a question, they were like, question, 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 and you said, input-output? That'd be a pretty good guess. And that person would probably be like, yeah, that was very deep of you. That's correct. It is input-output. So, now let's try number 9. Number 9, we're going to continue using the exact same notation, f circle g of 3. I'm going to rewrite that by definition. That's f of g of 3. So let's go find g of 3. All right, we need to find g of 3 first. So what is g of 3? G of 3 means go to the g function and look for what? The input of 3. There's my g function. My input is 3. My output is 2. So now I'm just going to replace g of 3 with 2. All right, so I just looked up g of 3 on the list they gave me. I could have looked up g of 3 on my table of values. There it is. G of 3 is 2. Or I could have looked on my graph, which I didn't make. So now what's f of 2? Now we go look up f of 2. I can look it up in my table of values. F input 2, output 4. Or I could go to my original function definition, f of 2, input 2, output 4. By the way, the answer is 4. There's nothing new here. It's just seeing different ways of representing a function. A function can be a list of coordinates, a function can be a table of values, a function can be a graph, a function can be an equation. So I'll go to, I'm sorry, not to 10. And number 10, we have f of 0. So f of 0. So you go look it up. So that means look at the f function, and the input is 0. What's the output? So looking on your list for f, looking at f, if your input is 0, your output is 1. So now I replace the f of 0 with 1. And now I go look up f again, and I look for the input of 1. So I go to my f function, I look at the input 1, output 3, and that's 3. Now, sometimes right about now, I try to really think about you folks and what you're experiencing emotionally and everything. You might be looking at this like, what are we doing? This is insanity. I mean, this is just a bunch of symbols. What are we doing? What is this good for? And sometimes, it's about building our vocabulary. Right now, we're building our vocabulary. We're building our ability to read a sentence, to read a command, to look for an answer. These aren't all that deep or, it's not like a good application problem. We're just seeing how to do things. Now notice in number 11, they don't do the circle notation. They just give it to us already, G of f.
Is that another way Right.
For some reason, when you said what is good for it, it's not some word.
What?
Is that another way to write?
Yeah, yeah. I mean, that is the definition of how to write. That's always what we write second.
Okay.
Yeah, yeah. So now they're saying, I mean, really, again, you can exaggerate G of f negative 3. So you're gonna look up f of negative 3. For f, the input negative 3 gives an output of 4. And then what?
G.
You go to G, you go to the input 4. Where's the input 4? What does that mean?
Undefined?
Undefined is the exact word. It's literally not defined. They did not define it for us. They did not give us that information. So you can say undefined. You can say not enough info.
Yeah. Is there any way to like find out what the? It looks like they're just random as far as like the coordinates, but would you be able to find out? You know what I mean? Like say, there's a word I'm missing here.
Could you extrapolate?
To find the next.
You can extrapolate,
Like
but
you know how we're like 0, 1, 2, 3.
Yeah.
We go like 4. 5.
yeah. It's given any pattern in mathematics, there are infinitely many functions that would fit that pattern and generate a new point. So there's no way to guess with any certainty.
Without having that.
Yeah, and this is I believe this is the definition of agnosticism. I don't have the information to make a decision. You know, I can't sit here and tell you what it is because I don't have enough information. So I reserve judgment. I'm not going to state what I think it is because I don't know. So I just say it's undefined. Okay, and then last one, number 12, G of negative 2. Which by definition is big G of G. Good. Like, oh, good. Let's go. Sweet. It's working good? How's all this good? Pretty good. Excellent. You're all graph. Nice.
Negative 2. 0? Because it comes up the negative 2 yeah, look once from there.
Did anyone get 0?
Yeah.
All right.
It's coming back.
It's coming back?
Yeah.
Oh, you remember doing this stuff?
What's the switch?
G times G.
It's G of G.
I don't know, I think so.
So this is we have a function, I would say f of 5. In this case, we have 2.
That's what I didn't.
So your first G is what? Negative 2, right? So we
You
give
like the
okay. So what do we put? What's the G, right? What's the second G? I want to make sure that you know it's the lowest question.
All right, folks. Shall we try the next set? Now, for all of these, keep in mind, always your first step is just to rewrite it according to a user-friendly definition. G circle F, I don't even know why they have that notation. It's so not user-friendly. It's just supposed to represent the final answer. But always the first thing we would do is just rewrite it as G of F1. So that you actually have something concrete that you know you're about to do. You're about to go find the answer of F1. So now how do we find this answer from just a graph? Keep in mind, that's input. And which axis is input? Yeah, X is always the input axis, Y is the output. So if I want to find F of 1, notice this is my F graph, this is my G graph. I go to my F graph, my input is X, my output is 2. Now Y, input X, output Y, so input 1, output 2. So you always go to the X, go up to the coordinate, and then go to the left until you hit the Y axis. So F of 1 means input 1, output 2. So now I have G of 2. So then I go over to the G graph, and I say, hey, G graph, input 2, output 3. And theoretically, this is almost fun. You know, once you feel comfortable with it. At first, it might feel a little awkward. So again, just to demo f of 1, I go to my f graph, input 1, output 2. And then I want g of 2, go to the G graph, input 2, output 3. So you're always starting on the x-axis, going up to the coordinate, and then left to the y-axis.
So this one will be a gradient. Table.
Yeah, you could turn this into a table of values. Absolutely, you could. As Emily mentioned, like for the first graph there, f of x, you could just turn that into a table of values. So here's my f function, where I just look at every coordinate. First coordinate is 0, 4. The next coordinate is 1, 2. The next coordinate is 2, 3. The next coordinate is 3, 3. And the next coordinate is 4, 0. Right, Emily, is that what you mean? Yeah. You can just write down all the coordinates.
Okay.
Yeah. You know, I always think of mathematics as just a bunch of definitions.
Right.
Like if you just know the definition, you just do the definition and the answer falls out. But it's really important to know the definition and do the definition. And that's all we're really doing here is we're just following the instructions of the definition. The definition says, rewrite this as f of g of 3. And the definition says, plug 3 into g. And the definition says, go to the input of 3 and the output therefore is 0. So you write down a 0. And then the definition says, plug 0 into f. And then you go to the f function and you plug in a 0. And the output is 4. That's the definition and that's the answer. It's like definition, definition, definition. And so there's nothing to understand about mathematics, but rather you have to know the definitions. And I've always applied that to math, but never to anything else. I wonder if I can apply that to my 2-year-old. You know, like she stomps her feet and collapses on the ground and gives me a pouty face. I wonder what that's the definition for. If I could just find out the definition, then I know how to, you know, work that.
Could be a definition of just being a brat.
Nah, I don't know. I mean, it could be.
Or the example would be, or
Maybe a tantrum.
food or water.
But see, that's the thing. Motive there is a subtle definition that we just don't know. And tantrum and brat is just kind of catch-all phrases that we use for something we don't know the definition of. I don't know. All right, so f of 1. Now again, this can be fun because you're cycling around on a graph. So I would definitely use your finger. So you can say f of 1. So I plug in 1 and I go 2. So then that becomes f of 2. And I go back to the f graph and I plug in 2 and 3. So when you all are done, I have a bonus question for you. Yes, Melania.
Why did 14 is,
Where?
wait, what, 14, why do you have 0?
Well, when I look up g of 3, I went over to g. Here's my g graph. My input 3, where's the coordinate? 0, which is a y output of 0. Good. Look, did everyone get 0 for the last one? Or maybe you're still working on it? What questions are running around in your mind?
Last one we had. So if my x, for the first one, my x is 1, so I go to 1, the
You're talking about
x
number 16?
Yes.
Okay.
So my x is 1, I go up, my y is 3, my y is 3 for that one, then I go down to the x and my x is 3.
Yeah.
Which makes my y 0.
Correct. That's it. You got it. You exactly walked us through that answer. Was that a question? You just want to clarify.
Yes and no.
Okay. Yeah, you got it. That's correct. Okay, so here's a fun one. So we have this notation called f circle f of x, right? That's the notation, right? And x is a placeholder for whatever I want to plug in. So what can I plug in right there? I can plug in anything. So what if I plug in f of x? So then what is that thing? What would f circle f of f of x be? So you'd have the big of x, right? So I mean, it's like a triple inception. Looks kind of weird, but that's what it would be. And imagine what that would look like on a diagram. You've got your original input following a function input of f to become f of x. And then that becomes the input of the next application of f. So you have f of x. And then that output becomes the input of the next application of f. Until you have f of x. And so this all the way shortcut is going to be f circle f of x. That's not important to know or understand. I just wanted to throw it out there, like it's like a little mind blower of again what we're trying to do. We're trying to shortcut doing something over and over again and just do it once. So what would be even more cruel to put right here? Oh yeah, go ahead.
Can you only have one
Circle.
like, so you see how like it's no, not necessarily circle. So at the top it's f of f and then x. You have more than one x, like, or is it just one?
It's typically a single variable. Yeah. Now what can I put here?
Infinity?
Okay, you can put it in infinity, although infinity is not a number to plug into a function, but you could for fun. Right here, I'm
Okay,
going to put
9,999.
The whole thing.
yeah. And then what would that be? The chicken. Yeah, I mean, it hurts the brain a little bit, right? So that would just be f of f of f of f of x. Like a little Russian doll. What are those things called?
Just ignore that.
Hatch dolls?
Hatch dolls?
He seems to ignore the wrong forever.
Yeah.
Russian nesting dolls.
Nesting dolls. There we go. That's exactly right. These are Russian nesting dolls. These are nested functions. In fact, I think you can call it a nested function. In calculus, we refer to them as inside functions and outside functions. And you can vary as many inside functions inside of other functions as you like. All right. So now we begin inverse functions. Now there's a lot of definitions up here. I'm not going to read through them all. You can always feel free to go back and read the individual definitions. I'm just going to show you some of the definitions. And I'm going to start by reminding us our definition of a function. Because there, look at the first example. It says, show that the given function is one-to-one, and then find its inverse. So first of all, what is a one-to-one function? Let's all recall that at some point we learned the definition of a function. And for a function to be a function, we learned that the function had to pass a certain test. So that's two functions. Let's go. The vertical line test. So this function right here, is that a function? Yeah, because it passes the vertical line test. No matter where I draw a vertical line, it only touches it once. And to be fair, what that really means is that every input is associated with exactly one output. Right? You could never have 5 going to 8 and 5 going to 10. It'd be very confusing if one input should cause two different outputs. So you can't have two coordinates stacked on top of each other that has to pass the vertical line test. Whereas here, I do have two coordinates stacked on top of each other. Like if that's the coordinate 4, then that'd be like having the coordinates 4, -3, and 4, 8, and that's just not okay. So this is not a function. This is a function. There. Now that's just the definition of a function. You need to pass the vertical line test. That makes you a function. So what's a one-to-one function? A one-to-one function. That means that you have to pass as well the horizontal line test. So here's a function. And then here's another function. Now, which one of these passes the horizontal line test?
The first one.
The x cubed plus 3.
Yeah, that could be it. So horizontal line test, this one passes the horizontal line test, whereas this one does not.
Which function have you ever seen has passed both?
Well, this one. This passes the horizontal line test and the vertical line test. Yeah, and in fact, that's what we want to do. Starting right now in section 5.2, we only want to talk about functions that pass both tests. So let's just look. What if, so here's one that passes neither, a circle. A circle fails the vertical line test, fails the horizontal line test.
Yeah, I tried to do that too.
Yeah. Here's one that only fails the horizontal line test. So it fails the horizontal line test. It's a function, but not a one-to-one function. Here's one that passes the horizontal line test, but not the vertical line test. And then here's one that passes both the horizontal and the vertical line test. So what are these things called? This thing is called terror. I'm just kidding. It's just not something we would study in calculus or otherwise. Because it's not a function, it's not a one-to-one function. We would want to change that a little bit to study some part of it. This one is a function, because it passes the vertical line test, but it's not one-to-one. This one is not even a function. So you can't say that it's what passes the horizontal line test. It's not even a function, so it can't be a one-to-one function. It's not even a function. Whereas this thing is a one-to-one function. It passes both. So in mathematics, and especially in calculus, we want to study things that are one-to-one functions, because the best part about them is that they are invertible. Only one-to-one functions can you find the inverse. You can find the inverse. And we want functions that you can find the inverse of. Yeah, it's very handy in calculus to be able to find the inverse function. And in a lot of other application settings, you want to find the inverse function. So, so there you go. That's the one-to-one function. Now, I'll tell you one more thing. When mathematicians want to study a function, and I'll just jokingly show you the circle again. Because there are times when you'd want to study a circle. The circle's a really nice shape. But unfortunately, it fails the vertical line test and the horizontal line test. And so what a mathematician would do is they'd say, well, I would like to study the circle, but it fails the vertical line test and it fails the horizontal line test. So what it'll do, I'll just study that part of the circle. Just this part. And then game back on again. So I'm just studying that part of the circle, but hey, it passes the horizontal line test, passes the vertical line test, and now that thing is a one-to-one function, and I can study it very neatly and cleanly. So that's what we do, and that's called narrowing your domain. That we're only looking at the domain, not all the x value inputs. We're not going to look over here. We're only going to look at this part of the domain, and then we're only going to look at the top part of the circle. Okay? So that's how mathematicians cheat. If you have a function that fails, you just narrow down what part you're looking at, and then it passes. Does that seem a little cheap? I don't know. That's how we do it. All right. So what's our goal then? We're going to look at a bunch of functions and try to find their inverse. Why would we care about finding their inverse? It allows us to ask more questions. So let's just remember real quick. The definition of an inverse, so here's my function f, and let's just say that I had a function whose input was 7 and the output was 14 and the input was 8 and the output was 20. The inverse of that function would be a function where if I input 14, I output 7, and if I input 20, I output 8. Okay, so automatically these are inverses. And the notation for that is f to the negative 1.
Just like cosine. Or cosine.
Yeah, kind of like cosine inverse. Yeah, exactly. It's just like that.
Are we studying that?
Not in this class.
Okay.
We always use the notation to the power of negative 1 to represent inverse. This is very unfortunate because x to the negative 1 already has a meaning, and it means to take the reciprocal. Right? Like x to the negative 2 means 1 over x squared, and x to the negative 3 means 1 over x cubed. And so anybody who would see f to the negative 1 would think, oh, that means 1 divided by f. But no. F to the negative 1 means the inverse function. I wish I could go back in time a couple hundred years to the meeting where somebody was like, let's just write -1 and call it the inverse. And I'd raise my hand and say, how about we just write a little I? That'd make a lot more sense. Now I know that that's the inverse of f, but no, no one does that. And maybe they had a good reason, and I don't know.
No one could go back in time.
Yeah, that's the one thing I would do if I could time travel back, is convert that to an I. So f to the -1, we don't say f to the -1, we say f inverse. So if this is our function, this would be our inverse function, and we notate it by a little -1. So that's what we want to do. We want to find inverses, but we're only allowed to find inverses if it passes the 1-to-1 test, which means it has to pass the horizontal line test. So how many functions do we have to look at?
At least 2 or whatever.
We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
You just got that right.
So there's quite a few.
Yes.
And we want to know, do they pass the 1-to-1 test? Do they pass the horizontal line test? So how should we do it? Exactly, just graph it. We all have graphing calculators. So I'll go ahead and start showing them to you.
I feel like number 1 is definitely going to pass because it doesn't have a square root, so it's not a problem.
Exactly right. Number 1 is 6x minus 2, which is a straight line. And a straight line, unless it's horizontal, is going to pass the horizontal line test. So let's look.
Since you're going online right now, what's going on with Wi-Fi recently?
I have no idea. It's been really messed up lately. So folks, does this graph pass the horizontal line test?
Yes.
Yeah.
We think so. What if I zoom out far, far, far,
We
and then
still think
eventually it loops back up on itself? Does anyone think that's going to happen?
so. We just narrow it. We still think
Well,
so.
that's true. We could always just narrow it down again. But in this case, we
No
know.
one has to know.
Yeah, we know it's not going to loop on a straight line. It's never going to curve. So yes, this one is 1-to-1. Now, go ahead and mark that. Next to each function, you don't have to write out 1, 2, 1. That's very long and annoying to write. So you just write 1, 2. It's 1-1. You can just write 1-1, and therefore it is 1-to-1, and therefore it is invertible.
Do we have to explain why in other ways?
Nope, you don't have to explain. We're just kind of doing this together
That's it.
as a group. Yep, it's 1-to-1. Let's look at the next one. We've got x minus 2 over 3 plus 4. How about that one?
Still good.
Still good. Yep. We can zoom in and out, but it's still just a straight line and say, yes, it is 1-to-1. How about this next one? Square root 3x minus 1 plus 5. Yeah. Does this one pass the horizontal line test? Sure looks like it. We could have some anxiety over, well, if I zoom out far enough, is it ever going to loop around on itself? But no, this one also passes the horizontal line test. How about the fifth root of 3x minus 1? Now, first of all, how do you do a fifth root? Well, folks, you've probably, just like you need to know definitions like a negative exponent, you've probably seen before that the square root of x is actually, so that's the square root of x, that's actually x to the 1/2. And the cube root of x is actually x to the 1/3. And the fourth root of x is actually x to the 1/4. Have you seen this? Does it ring a bell? So the fifth root of x would be x to the 1/5. In general, the nth root of x is x to the 1/n. So notice I have to be very careful when I type this in. 3x minus 1 to the power of parenthesis 1 divided by 5. And so then that's my function. Does that pass the horizontal line test? Yeah, it does. Okay, so far so good. The next one is 3 minus the cube root of x minus 2, which is x minus 2 to the power of 1/3. Does that pass the horizontal line test? Yeah, any horizontal line would only touch it once. How about this next one? 3x plus 4 squared minus 5. No, it does not pass the horizontal line test. However, what did they write? They said when x is less than -4. So what are they saying? They're saying consider the vertical line x equals -4 and only look to the left of that.
Now, if we only look to the left of it, is it all passing the 1-to-1 horizontal line test? Yeah. So there's your first example of mathematicians saying, well, let's just look over here. Let's not look at the whole thing. Let's just look over there. So that also passes the 1-to-1 test. How about, let's keep going here, number 7. X squared minus 6x plus 5.
X is greater than.
Yeah.
Same problem.
Yeah, as a whole, no. But if I'm only looking to the left of 3, then yes. Still passes the horizontal line test. How about,
I'm assuming number 8 is going to do the same thing.
you're assuming, oh, actually, yeah. Number 8 is also 1-to-1, passes the horizontal line test.
It was a hypothesis.
It was a hypothesis, 2x minus 1. I wonder if they're going to give us any that fail. 3x plus 4, does that pass? Yeah. And then negative 3x minus 2. X plus 3, that also passes. Yeah, so they all are. And that's the whole point, because they want us to now find the inverse. And you can only find the inverse of a 1-to-1 function. So now all of those problems are ready for us to go find the inverse. So let's just remember, what are we trying to do? Whatever function they give us, we want to find a new function that will reverse the role of input and output, that will effectively reverse the 2 columns. So there's 4 steps. We're going to write them down nice and neat for each problem. Here's number 1. I'm going to write down step 0. Write the problem. Right. So I have to write it down because you have it on your page. But the original problem is f of x plus 6x minus 2. Step 1 is replace f of x with y. So it's really y equals 6x minus 2. Now keep in mind, f of x and y are synonymous. They both mean the same thing. If x is the input, then y and f of x are both the output. Right? X is the input, y is the output, f of x is the output. Now remember, what's the definition of an inverse? An inverse function does what? Flips the role of input-output. So everyone look, x is the input, y is the output. So if we wanted to find the inverse, and we want to switch the role of input-output, what would be a reasonable thing we could do right now with the x and the y? We would switch them. And that is, in fact, what we're going to do. Switch the x and the y. So you just keep the equation just as it is, but everywhere you see a y, you write an x. And everywhere you see an x, you write a y. Now, I know that math is oftentimes filled with these rules that seem so arbitrary. This was not an arbitrary thing. The definition of the inverse is to switch the role of input-output.
Huh? I just remember saying about switching roles. What did that sign that I showed you before, wouldn't that kind of fall into this?
Sign.
Yeah. Almost like a very extended S.
Oh yeah, the S. I don't know. Now, let's talk about it more after class. So you mean switching the role of input-output?
Yeah.
I don't know. Off the top of my head, I don't know. So we'll explore more later. Okay, so now that you've done all that, and keeping in mind everything we've done so far is just very formulaic. We wrote down the problem, made it a y, and switched the x and the y. So now what we're going to do is solve for y. It's kind of like this little buried treasure. I mean, we started with y already solved for, and now we just threw y into a new problem, and now we have to solve it. So now we're about to do some algebra. So while we do this, let's kind of review algebra, right? How does this work? Y is the letter we want to solve for. So you look at that letter and you tell the story of y. You say, well, what's happening to y? Y is being multiplied by 6 and subtracted by 2. So what do we do first? Add 2. Yeah, we add 2. This is how algebra works. You look at the variable you want to solve for, you look at what's happening to it according to PEMDAS, parentheses, exponents, multiplication, divide, add, subtract. Y is first being multiplied by 6 and second being subtracted by 2. Whatever you said last is what you do the opposite of. So we add 2 to the other side. So now we have x plus 2 equals 6y. And then you tell the story of y again. You say, what's happening there to y? Y is being multiplied by 6, so you divide by 6. That's algebra, right? I mean, that is the very definition of algebra. So we have y equals x plus 2 over 6. And what you'd want to do is switch, go back to putting y on the left, y equals x plus 2 over 6. And then the very last step is to replace y with f inverse. So this is actually now the inverse, f inverse of x equals x plus 2 over 6. So we have this neat and tidy chain of steps where we start with f of x and we end with f inverse of x. Now, I claim that we just produced an inverse. How could we check? Plug in what? What is an inverse supposed to do? It's supposed to flip the input and the output. So what we could do is we could say, well, if f of x is 6x minus 2, and I claim the inverse is x plus 2 over 6, then in theory, if I just pick some totally random out of the blue inputs over here, like even more random, choose a totally random number between 1 and 100.
It's -2. Oh, you said 100?
Well, that's fine. -2 is fine, and 15. Great. Okay, so I mean, these are completely random numbers essentially. So let's find their output. If I plug in -2, 6 times -2 is -12, minus 2 is -14. If I plug in 15, 6 times 15 is 90, minus 2 is 88. So if that is the inverse, then I better be able to plug in -14 and 88, and it should give back those numbers. So let's try. If I plug in -14, -14 plus 2 is -12, -12 plus 2 is 90, 90 divided by 6 is 15. So at least for the couple of numbers we tried, yeah, these do appear to be inverses. Have I proven it to you? I mean, maybe I just happen to choose some pretty good numbers. Well, yeah, no, that's a good point. You could graph it. And we haven't talked about what properties inverse functions have yet as a graph in terms of flipping the role of input and output. But yeah, so at this point, we have some level of confidence that that really is an inverse. But you never know. I mean, if I keep trying numbers, like maybe I try 37, and then I eventually get to a number that doesn't work. And I'd say, oh, darn, it looked like these were inverses, but they're not. So we're going to give you 3 definitions of how you know that this thing really is an inverse. And the first definition is following these steps. If you follow these steps, you're guaranteed that what you get is the inverse. Some confidence can be gained by just trying a couple inputs and seeing if it works. So let's try the steps one more time. Let's try number 2. So we had f of x. Oh, sorry, steps here. I'll write down the problem. Oh, nice. Okay, so what's the first thing we do?
Replace x with y.
Yeah, replace f of x with y. And Nadine, what's the next thing we do?
Wait, so.
Step 2.
Change x.
Yeah, switch or exchange x with y, so now I have x equals y minus 2, that's 3 plus 4. And then what do we do, Emily?
Oh, are you?
So the resulting equation.
Yep. Yep, so now solve for y. So we have to, again, go through algebra. So algebra says to look at the variable you want to solve for, tell the story of it according to PEMDAS, and then start at the end. So y is being subtracted by 2, divided by 3, and adding by 4. To subtract by 4. So now we have x minus 4 equals y minus 2 over 3. And algebra, you just do over and over again. You keep telling the story of y until you finish. So y is being subtracted by 2 and divided by 3. Multiply by 3. So multiply both sides by 3. Be very careful that you use parentheses on the left and that you see the cancellation on the right. And I'm going to go ahead and distribute already. So I have 3x minus 12 equals y minus 2. And now again, you tell the story of y. Y is being subtracted by 2, so you add 2. Add 2. All right, so we have y equals 3x minus 10. Then what do we do?
Substitute x.
Yeah, so now I'm gonna, step 4, I'm gonna rewrite that now as y equals 3x minus 10. Then replace y with f inverse equals 3x minus 10. Now I think you might have some more room on your paper there. I'd like to go ahead and give you now the formal definition of knowing that these things really are inverses. And maybe you want to write all this down. Maybe. For sure. Write it all down. So, claim f of x equals x minus 2 over 3 plus 4, and f inverse of x equals 3x minus 10 are inverses. Okay, we'd like to show for sure that those things really are inverses. We could gain some confidence by simply doing a table of values real quick and seeing what we think. So like for instance, I'm going to try the input number 14 on f. If I input 14, 14 minus 2 is 12, 12 divided by 3 is 4, 4 plus 4 is 8. So now I'm going to try f inverse. What happens if I plug in 8? Then 3 times 8 is 24, minus 10 is 14. And yeah, like as of right now, by choosing my totally random number, I do have some confidence that these are inverses because it immediately reversed the role of input and output. Okay, so here's the definition. For two functions to be inverses, two things have to be true. Both f of inverse of x has to equal x, and f inverse of f of x has to equal x. So you notice what I just wrote down as a function composition. Now what we're saying is that if you plug the inverse into f, the answer should just be x. And if you plug the function into the inverse, the answer should just be x. Meaning that whatever input you plug in, you just get that same number out. And whatever input you plug in, you get that same number out. And what essentially that means is that f and f inverse canceled each other out, which was one of our original definitions of an inverse. Inverse operations cancel each other out. Inverse functions cancel each other out, such that whatever input you plug in, that's the output. Okay, so now we're going to do it. If I want to actually solve f of f inverse of x, first I write down f. The structure of f is something minus 2 over 3 plus 4. And what am I plugging into f? F inverse,
3x minus.
which is 3x minus 10.
Is this just, are we just doing this, or is it asking us to do?
It's not asking us. I just wanted to show you that
Alright,
this is the formal definition of knowing that you did find two functions that are inverses. And maybe this time around you just want to watch. I mean, that's understandable, but I think writing it down is good practice. So what do I have now? In my numerator, I have 3x minus 10 minus 2. That's 3x minus 12 all over 3 plus 4. And then from the top, I can factor out a 3. So that's 3 outside of x minus 4 all over 3 plus 4. And what can I do with my 3's? Cancel them out. So x minus 4 plus 4. And then what? And they cancel out, you get x. So yeah, that one did equal x. So the f of f inverse does equal x. So far, so good. But now I have to try the other way. So now I'm going to do f inverse of f of x. F inverse, the structure is 3 something minus 10. And into that, I will plug the function, which is x minus 2 over 3 plus 1. So my question is, does that end up equaling x? Well, first I would distribute my 3. So that would be 3 times x minus 2 over 3 plus 12 minus 10. And then my 3's cancel out, and I have x minus 2 plus 12 minus 10. And negative 2 plus 12 is plus 10 minus 10, which is x. So I realized I did that kind of fast. I just really wanted to demonstrate it for you. But that's the definition. The definition of being absolutely certain that you have the inverse is that they should cancel each other out in both directions. And so that really proves that we do have two inverse functions. What are your thoughts from, I'll keep the steps up there. So we've seen now the steps that you can gain confidence by trying some random values, but that this is actually the definition. Now, Valeria, when I asked how do you know if something's an inverse, she said, look at the graph. And I really appreciate that she said that, because I feel like so far in the last months together, I always said, what should we do? Look at the graph, because why not? So let's look at our two graphs of both problems and see what we notice. So the first problem was what? 6x minus 2, and what was the inverse? X plus 2 divided by 6. What do we notice about these graphs? Maybe nothing, but what do we notice?
Oh, okay. It's not flipped, it's like rotated.
They are rotated, they are flipped, and it is a reflection across the line y equals x. So y equals x is a diagonal. Do you see that if you turn your head to face the green line, if you turn your head and face the green line, they are mirror images of each other. And that's the property inverse functions have. Inverse functions are reflected across the line y equals x, which once again is a demonstration of reversing the role of x and y. By reversing the x and y axis, you're flipping it across the line y equals x. That was one example. Let's do the second one. So our next one was x minus 2 or 3 plus 4. And then the inverse was, I erased it.
3x.
3x what? Oh, minus 10? Yeah, so how about them? So let's kind of just take some notes about that, because the class is almost done here. Like inverses. What do we know about inverses? Reverses the role of input-output. Must be 1-to-1, meaning passes the horizontal line test. These are all just good facts about inverses. We can solve for an inverse by following the 4 steps. So follow 4 steps to find the inverse. By definition, f of f inverse of x has to equal x, which also has to be f inverse of f of x. So they both have to equal x. And finally, they are mirror images across the diagonal. Line y equals x. So visually, you can always tell if you're looking at inverses. These are all just some nice facts about inverses and everything that we've come up with. Keep in mind, one of the original reasons we wanted an inverse is simply to change the way you ask a question. You could say, if I work 10 hours, how much money will I make? Or you could say, if I want to make this much money, how many hours do I have to work? Right, so we're allowing ourselves, by finding inverses, we're allowing ourselves to ask questions in the reverse order, which again is input, output. And the whole reason that we kind of looked at function composition was in order to come up with a test that two functions really were inverses. Namely, that you'd have to compose the function with its theoretical inverse, and if you do that both ways and they both equal x, then you're guaranteed for sure that you have an inverse function. Because inverse operations and inverse functions cancel each other out. And otherwise, we reached a really good spot today, folks. You know, depending on how you feel, please feel free to ask me questions right now or leave. When we come back next time, we'll do more solutions like that, and we'll move on. Really nice, folks. Welcome back from spring break. Golly gee, it feels like I haven't seen you in 2 weeks. Oh, wait, I haven't seen you in 2 weeks. Congratulations, Lee, on becoming a married man.
Thank you.
It's very exciting. Lee, did I ever tell you the conversation my wife and I had about how many kids we're going to have?
I like it. I like it.
I was trying to think what advice I could give you when you get married. I mean, I've only been married for 5 years. So there's a conversation we had. She wants to have 4 kids because she's one of 4 siblings. I wanted to have 2 kids because I'm one of 2 siblings. So we compromised on 4.
They're gonna say 6.
What's that?
They're gonna say 6.
Oh, yeah, no. No, but I gave the definition of marital compromise. Do what she wants.
Right. Always.
Hay una